Okay, this video is about an AC generator. Okay, AC generator. AC stands for alternating current. So this is a generator that will produce current, but it's a current that keeps constantly changing its direction. So it's an alternating current. Let's see how it works. So here we have the north pole of a magnet, and here we have the south pole of a magnet. So we know that the magnetic field is going to be going to the right. Now it leaves the north pole, goes to the south. So the magnetic field goes to the right. Between the poles, what we have is this loop. You see this wire here is a loop. It's being held by this armature. The role of this armature is just to keep constantly rotating our loop. Okay? So we have these wires here that will connect to our device, the one that we want to turn on. And so these wires then go all around here, form a loop, and then come back, and then it comes back. Since it's constantly turning, we are going to induce current. Why? Now, how are we going to induce current? Remember that we induce current by changing magnetic flux. We are not going to be changing the magnetic field. The magnetic field from north to south is constant here. We are not going to be changing area. The area of this loop is constant. But what will be constantly changing by rotating this loop, we are going to be changing the angle. Now, the angle between the magnetic field and the perpendicular direction of our loop. So we know that when our loop is parallel to these lines, the lines of the magnetic field, the magnetic flux is zero, right? Zero. So I'm going to start from this scenario where the magnetic flux is zero, but since I'm rotating, there will be a point where my loop will be perpendicular, and that these lines will be crossing the area of my loop. So I'll have a strong, a large magnetic flux. So I go from parallel, zero magnetic flux, to perpendicular, strong magnetic flux. This change, where we increase the magnetic flux, will induce current in a certain direction, and we'll see this next. But there is also the other way around. Here I'm now perpendicular. I have a strong, large magnetic flux, but if I keep rotating, there'll be a point that I'll become parallel. So I'll be going from strong, large magnetic flux to zero magnetic flux. So now I'm making this magnetic flux weak. And this change will also induce a current, but now in the opposite direction. So that's what is going to happen. We'll constantly change in the direction. At one moment we have current going from A all the way to B. In the next moment we have the current going from B all the way to A. And then again A to B, and then B to A. So that's why we create this alternating current. So you see that the cause for this current in this case, in this AC generator, is the change in angle. No area, no magnetic field, is the change in angle that will give us this change in magnetic flux. Now you can ask, what is the origin of this? What is the energy that we use to create electricity? Because that's what the generator is doing. It's transforming some kind of energy into electrical energy. Well, which kind of energy is being transformed? How, or in other words, how do we rotate this loop? There are different ways to do that, to generate energy that will be rotating this loop, and then from this rotation we get electricity. For example, if you think about a hydroelectric, how do you get this armature to rotate? Well, you have your waterfall. Your waterfall transforms potential energy into kinetic energy. Now the potential energy, once as the water falls, it rotates our turbine that will then rotate the armature. Okay, but there are of course different sources of energy. You could, for example, burn coal or nuclear energy and other alternatives. Okay, wind is another alternative. Okay, so what I want to do now in this on the right side with this video is trying to show to you what I've been talking about. So first thing, you will see this is marking the direction, this instrument here is marking the direction of the current, and you will see that it's constantly changing as our loop keeps rotating. Look at this, you see, and one moment is to the right here the current, And if we wait, I don't know, it's too slow. It didn't. Okay, so here, yeah, you see, so the current is constantly changing directions as we rotate. Okay, so now I want to show to you how we determine the direction. Okay, so let me go a little bit forward. Okay, so there we are. We are going to start rotating this loop. For some reason it's so slow. Okay. All right, so let's pick this case. Let's pick one case where we are parallel to the direction of the magnetic field. Let me wait. Okay, so here we are. We are in this direction and parallel to the magnetic um, field. The magnetic field goes from north to south. So my loop is here parallel, magnetic flux 0. As I keep rotating, I'm going to go to the scenario where now we are perpendicular. Okay, so I had magnetic flux was 0 to now a case where the magnetic flux became very strong. We have lines going from north to south crossing the area of the loop. How do we oppose to that? Well, you see, if I induce a current from D to C, you see that I'm going to induce a current. No, if we have this current going from D to C, you see, so put your thumb going from D to C. You see that your four fingers will go into the loop to the left. Okay, so we have more, because we are rotating, we have more and more fields, lines of the field going from to the right, not from north to south pole. And so we induce a current going from D to C to oppose to that. And so we create magnetic field that goes to the left. Do you understand? So put your finger there and you will see that you got magnetic field going to the left. So to induce this change, this increase in the magnetic flux, we induced a current that goes from D to C. Okay, but we keep rotating. So now let's stop here. We have now the plane again parallel, no? Our loop again parallel. So 0 magnetic flux, and we are going to keep rotating. So now we'll have this scenario where we are perpendicular. But now you see what is on top is A and B. So to oppose this scenario where we went from 0 magnetic flux to a strong magnetic flux, I'm going to put a current. I will have an induced current that goes from A to B. Put your finger there, put your thumb from A to B, and you see your four fingers inducing, creating magnetic field that goes to the left. No? So this will be opposing this change, this increase in magnetic flux. And so you see that at one moment we had current going from D to C, and now we have so the current was going D to C to B to A, and now we have current going from A to B to C to D. So this is the alternating current, constantly changing directions.